A production server hits a wall. Alerts trigger as a monolithic Java application suddenly demands 99% of the CPU, bringing system operations to a halt. The kernel sees massive resources consumed by one Java process, but visibility ends there. Because the JVM manages its own thread scheduling and memory, the OS treats it as a single opaque entity, unable to distinguish the internal execution paths. The immediate operational reflex is restarting the service to clear the CPU spike and restore functionality. Restarting the application instantly destroys the volatile RAM and the execution state. It erases the exact forensic evidence required to fix the underlying code flaw. Relying on guesswork and reboots leaves the system vulnerable to the exact same failure. Instead, true resolution requires a rigid, deterministic funnel of isolation. We have to pierce the JVM abstraction layer without killing the application, mapping the OS-level symptom directly to the root cause in the code. Effective troubleshooting bridges the gap between how Linux schedules tasks and how the application executes its internal state. The isolation process begins at the Linux command line, using the top command. This simulated terminal shows how standard top output only provides a single row for the entire application. It aggregates all internal concurrency into one metric. To break the process down, we run top with the -h and -p flags. This expands the single process, displaying all individual threads inside the JVM. Scanning this list isolates the exact thread monopolizing the CPU. We capture its specific thread ID. That isolated identifier represents the exact execution path causing the system degradation. We have now located the culprit at the operating system level, but we still cannot read the application logic it is trying to execute. A strict formatting barrier separates the Linux kernel from the Java environment. Linux logs and manages all of its process and thread IDs using standard decimal numbering. This split-screen diagram highlights the mismatch. While the OS uses base 10, Java diagnostic tools track their internal thread identities using base 16 hexadecimal. Before we can search the Java environment, the decimal OS thread ID must be converted into its hexadecimal equivalent. This newly generated hexadecimal value is the native ID, or NID. This is the specific identifier the Java virtual machine uses to label its internal thread activity. This mathematical conversion serves as the exact cross-reference point, allowing us to step out of the operating system's domain and into the application's code. Execution states in RAM are highly volatile. It is impossible to manually analyze a thread while it processes thousands of instructions per second. We must force the system to freeze and dump its current state into a persistent disk file. There are two mechanisms for this: an OS-level core dump or an application-level thread dump. An OS core dump captures the total physical memory of a process during a kernel panic. For a CPU loop, extracting gigabytes of memory is entirely unnecessary. Instead, we execute the jstack utility, precisely extracting the specific thread states without crashing the live system. The output is a complete, static snapshot detailing exactly what every single thread inside the JVM was doing at that specific second. By writing this volatile RAM state to disk, we have successfully preserved the forensic evidence of the failure. Opening the jstack output reveals thousands of lines of dense Java stack trace code. To cut through the noise, we run a text search for the specific hexadecimal native ID we calculated earlier. Locating that ID reveals the thread's execution state. A status of waiting signifies a resource deadlock, while runepable typically points to an infinite loop pinning the CPU. The lines immediately following the ID and status display the exact Java class and method executing the infinite loop. The opaque 99% OS CPU spike has now been definitively mapped to a single identifiable line of application code. Generating the thread dump transitions the incident. It moves from an infrastructure problem to a software engineering problem. In the first tier of escalation, the exact stack trace is handed directly to the application developers so they can write a code patch. Occasionally, static code analysis fails, and the developer cannot replicate or identify the bug locally. The issue then escalates to a bridge call, convening L3 network engineers, OS administrators, and application owners to examine the live system together. At this stage, the team deploys dynamic profilers, advanced diagnostic tools that attach to the JVM to monitor live execution paths in real time. The final tier of escalation occurs when the analysis proves the bug does not exist in custom code, but deep within the vendor's JVM architecture itself. Opening a support case with a vendor like Oracle requires indisputable proof of internal failure, which is exactly what the jstack dump provides. The thread dump provides a definitive, point-in-time forensic record of the execution state. It serves as a shared piece of evidence that allows infrastructure, development, and vendor support teams to align on the same set of facts to force a resolution.